Great. Well, thanks for joining us for the third installment of our Dragon Olin lectures. Today we'll talk about how do you select the processes and materials for things that you're building. I'm Scott, the CEO and co-founder of Dragon Innovation. We're a company that helps people go from a functional prototype to high-volume manufacturing. And even before that, we can get involved and help you with crowdfunding as you prepare for a great campaign. And then after you're done with that, we can help you go and build your product. So one of the things we always think about as you've built a prototype and have something working is how do you take it to the next step and get ready to build a lot of them. And this is where things that may have seemed easy in prototyping really become incredibly important to get right up front, because the decisions you make early on are going to cast a really long shadow and will often dictate whether your product succeeds or fails. So one of the things we start thinking about up front is, what are the right materials? Should you build it out of aluminum, out of steel, out of titanium, which is always awesome, although expensive, carbon fiber? And then if you are building it out of those, how do you do it? Do you machine the aluminum? Do you extrude it? And so on. And with time, you can certainly figure this out with experience. But what I wanted to do today is work through a methodology of how to at least have a subset of different processes and materials to consider, as opposed to everything in the world. And this makes sure that you aren't considering things that aren't valid, but also that you're not too narrowly focused on just one technology. Like, we do a lot of stuff with injection molding, but there might be a very valid reason to use a piece of extruded aluminum, and you wouldn't want to neglect that just because you hadn't thought about it. So I'll start by talking about minimizing part count. And as you are making the transition from one to many, it's really critical to change your philosophy and get away from a prototype where you can stick on as many parts as you want because it doesn't take too long to machine them, to really think about integrating the parts and making a really efficient design. That's super important. In addition, as we think about minimizing part count, it gets important because if you don't have a part, you can't run out of it. So suppose you're building a product that had a special spring. If you, for some reason, forgot to order the spring, or the spring vendor had a bad day and didn't make it, then your whole line conceivably is stopped. Whereas if you've designed a part so that you don't even require that spring, then you don't need to worry if it doesn't ship because you don't need it. You don't need to carry it on the bill of materials. You don't need to pay for it. Your design just gets a lot more efficient. And also it saves a lot of time and effort because you don't need to have an assembly worker put it in place and deal with that. So always thinking about minimizing part count is a great place to start. We'll do this in two parts. First, I'll talk about calculating your assembly index of efficiency, which is just a good benchmark that you can use to really track how your design matures over time. The actual number doesn't really matter, but it's just, are we going in the right direction or the wrong direction? And then we'll dive into the specifics of picking out materials and processes. So first you want to calculate the theoretical minimum number of parts. And to do that, there's three questions you ask for each part. One, is there any relative motion? So imagine you had a lever that has to rotate. That's most likely going to be two parts because they have to rotate relative to each other. Second, are they different materials? So is one, say, needs to be a Delrin bushing, and then the other maybe is ABS for the strength of the arm. In that case, likely they're going to need to be two separate parts. And the third one is, when you're putting it together, is it such that the geometry would prohibit one part doing both purposes? So say, for example, you're building a consumer electronic product that's got a circuit board clamshell between two housings. Chances are the housings have to be separate parts just so that you can get the board inside. If the answer is yes to any of those, then the part's required. If the answer is no, then theoretically, then it's not required. So as you work through your design, you pick up your product and start taking it apart, and for each part, is it required or not? And you just keep track of that. Now to calculate the assembly index, it's a pretty simple formula. It's a percentage, which is based on the number of parts required, which is what we just calculated, the assembly time for those parts. And for this, you assume that it's 3 seconds per operation. And if you think about a part going down a line, so think of a Laverne and Shirley line where people are doing operations on it, you can imagine that to, say, add a screw into a clamshell, that's about 3 seconds with the screw gun, and then it goes on to the next thing. You shouldn't be spending 5 or 10 minutes putting something together, at least in a conventional assembly line. If you're doing a cell line, then it's a different a ball wax. And then you want to calculate actually how long does it take to put together your thing. And in that case, you take your product and literally start the stopwatch, put it together, and see how long it takes. If you didn't have the thing in front of you, say it was all designed in CAD, then you can do the mental experiment saying, oh, I think it's going to take 4 seconds to do this and 5 seconds to do this, and add it up. And then basically you just multiply the number of parts, minimum parts you calculated times 3 seconds each, and then divide it by the actual time. And what you should see to start off for a fairly low volume consumer electronic product or electrical mechanical is about 25%. So it seems like a low number, but it's not a bad starting point. As your design gets more and more efficient, so if you think of building a really high volume product, you'll probably get more up to 60%. So that's a good target. But the important thing is just seeing how you track over time, and you can evaluate the maturity of your design by making changes. Did you increase your overall efficiency, or did you set yourself backwards? Bob, you had a question?
Yeah, I was just wondering, the number of parts is sort of the functional number, not the number of fasteners that are required to pull it together.
Yeah, so for the fasteners, usually we would not, those are typically not counted as a minimum number of parts, because you can imagine often you could do a pole that you could cold work or heat stake together. So usually you throw out screws, and they're never a minimum part of the minimum required parts. But as you add them in, of course, then that's going to jack up your actual parts. Yeah, and again, it's you can never do a design that has exactly the minimum number of parts. Like, it's not physically possible, but it gives you a baseline. And it's also a great thought experiment, because it forces you to question everything. Do I really need 4 screws? Could I do it with 3 screws? Do I really need to make these separate parts? And that overall will make your design much better. So it's a great exercise to go through. Okay, so now jumping into the, how do we pick the processes and materials that we should build stuff out of? And again, a lot of this you'll get with experience, but this is just a great way to step through it. So you want to make the selection early in the design. If you had, say, designed something for titanium, but realized you didn't need that, the geometry is going to be very different if you use a different metal in the way you tool it and so on. So you kind of want to get this stuff right from the start. As we talked about, you want to consider all the options in front of you and not get too narrow too quickly. And this is we see people do this all the time. It's sort of like if you have a hammer, the whole world is nails, or if you know injection molding, you're always going to do that. It's a great opportunity to step back, because the decisions you make now are really easy to change, but once you're further downstream, it's a nightmare to change them. You also, because we always think about manufacturing things, you want to make sure that your contract manufacturer, CM, has the capability of doing this. So we do a lot of work in China. There's injection molding everywhere, so that's a really strong option. You could also do forging or extrusion, but you wouldn't want to pick something that your CM couldn't do, or you wouldn't want to pick a CM that couldn't do what you're trying to do. The part and assembly process and materials are really closely linked to how you process the material. They basically go hand in hand. You want to reduce the number of secondary ops. So what we'd say is the primary operation is like injection molding or die casting. A secondary operation would be, let's say you die casted a cool racing car, and then you have to fit it together, and maybe there's some screw bosses that don't line up perfectly. You may bring it over to the drill press and then drill those down, or whatever precision you need. The problem is that takes extra steps in material handling, because you've got to gather all the parts up from the from the die caster, bring them over, put them on a fixture, put in the drill bit, go through it, and then there's always a chance that you're going to mess it up and end up scrapping the whole part. So ideally, you'll minimize the secondary ops and pick a process that just gets it right the first time. And as we talked about, like, once you've bought hundreds of thousands of dollars of tools, you can't very easily say, oh, injection molding is not going to work. We really should have die cast it. Those are the things to think about up front before you set it in stone. And there's also a lot of great techniques to hedge your bets. So one of the ones I like a lot, and as I said, we do a lot with injection molding, is that ABS and polycarbonate are all in the styrene family, so they have the same shrinkage. And one of the things with injection molding, which we'll go into in a later lecture, is that the plastic will shrink down over time and grab onto the mold. So you really have to account for the shrinkage when you're designing the tools. Usually ABS shrinks about 0.5%. So you design the tools roughly 0.5% bigger than what you need. But everything has a different shrinkage. So polypropylene shrinks at a different rate, nylon shrinks at a different rate, polyethylene shrinks at a different rate. So you can't very easily change the material because that would totally change the geometry of the tool. But where you can get by is just remembering ABS and polycarbonate are both styrenes, and they both shrink at about 0.5%. So if you did need to do something that needed better impact resistance, you might start with ABS, and if it was shattering, then you can do a mix of ABS and polycarbonate, and then you could even go all to polycarbonate if you had to. There are some changes you'd have to make on your tool because polycarbonate flows like molasses in January, so you'd want a bigger set of runners to be able to accommodate it. But those are pretty easy changes. So if you think about it ahead of time, then you can get by. But it's better to plan on it and not have to, or it's better to be proactive instead of reactionary. Once you've made the decision, it's, if you imagine changing course with all of these workers and having them do something differently, that would be very challenging. So it's really, really important to get it right up front. This is just running down a Roomba line. This is actually only one of 4 lines that we had running. It's about 1,200 workers, where we build 40,000 Roombas a week. So just to emphasize kind of the importance of these decisions. You can see the Roombas on the belts and the different inspectors. This is an amazing resource for design for manufacture and assembly by the guys down in Rhode Island. The Boothroyd, Dewhurst, and a lot of this following material we'll talk about comes from their book, but I highly recommend picking this up. So material and process considerations. One, what's your production volume? Are you building onesies, twosies? Are you building 100? Are you building 500,000? If you're thinking about injection molding, you'd never do it for 1 or 2, but if you're building 500,000, it's probably a pretty good thing to consider. How much money do you have? If you've got a lot of money and building high volume tooling is good. The injection mold tools are these giant pieces of steel. If you have less money, you may consider other options. How long does it take? So if you're going to just machine something, you can do that pretty quickly. But if you're going to injection mold it, we typically say it's 6 to 8 weeks just to make the tools, and then you've got to debug the tools before you can make the parts. So that's great if you've got enough time, but if you need it done in 2 days, unless you use a company like ProtoLabs, it's probably not going to happen with injection molding. What's your experience and what design tools do you have? So if you have done a lot of injection molding, you certainly would want to weight that a little bit higher than different techniques. Part geometry is critical, which we'll talk about in a sec. Any sort of service or environmental requirements. So does it have to work in an acid bath? Does it have to work underwater? Does it have to be user replaceable? Does it have to be safe for a user? Those are all things you want to bake into your decision. And the aesthetics. Is it a cosmetic surface that people are going to interact with, or is it buried inside the device? And the accuracy. Is it a precision piece of equipment that has to hold very tight tolerances, or is it something that's a little bit more forgiving? So let's just run through an example here. We've got a generic, pretty simple piece here, and we've assigned a couple of different shape characteristics. So depressions are basically this groove in here, or you could think of them as grooves. Uniform wall thickness means that it's 20 of whatever units this is all the way around. So it does have a groove, the depression. It does have uniform walls. Uniform cross-section. So does it vary with the Z dimension? No, it's a straight. Does it have a axis of rotation? No, you can't spin it. It would be different. Does it have a regular cross-section? So this would be like a square, a rectangle. Basically a regular polygon. Does it have a captured cavity? So think of like a bottle in this case, where you wouldn't be able to pull an inner mandrel out. No, it doesn't. Does it have an enclosed cavity, which would be like a ball? And does it have draft? No. Does everybody know what draft is? Okay, draft is really cool. So if you think of injection molding, and the simplest form, you'll have two different plates and a cavity machined on the inside. That's the inverse of the part you're trying to build. And basically there's a giant screw that will squirt in the melt, which is the resin under temperature and pressure. It'll fill the cavity. But as you remember from before, it's going to shrink. And when it shrinks, it's going to hug really tight on the core. And if it had straight walls, you're never going to get it out. Usually what we'll do is have ejector pins, which if you look on the back of any plastic part, you'll see the witness lines or the little circles where it was pushed out. But regardless with it, no matter how many injector pins there are, if it's a straight wall, you're going to scratch it and it's going to squeeze very tight. So what we do is we put draft on it, which is a little bit of an angle, usually about 1/2 degrees. So think of like the cup in your hand. You can imagine how that has a little draft, and it will pop off nice and easy. So with this part, it's straight wall, there's no draft. All injection molded parts, though, if you look at them, will always have draft in them. So no draft, correct. And then just a few material requirements. So we fill out those parts, and then we've got this awesome chart, which basically for the different manufacturing techniques from solidification processes, which would be sand casting, injection molding, to bulk deformation, which is forging, extruding, to material removal, which is machining, profile, which is like electro discharge machining, and then to sheet metal forming processes. Basically, on each one of these different categories we discussed, it says whether it can support that operation or not. So if we work through it and basically cross out the ones that can't do, so I'll start with the depressions and start crossing out those, and then just work the way down our list, we'll see what's left. So basically, after that, we've got these 6 processes left available to us. And the thing I love about this is, ordinarily I would jump, everything I love in injection molding would jump on that. But this would say, oh, there's all these other things we could consider. And some of them you'll look at from experience and say, no, that doesn't make any sense. But at least it forces you to have that conversation. And then you can take that chart.
Is 3D printing changing any, I mean, that chart doesn't even have it on there.
That's right, this is old school. Yeah, 3D printing, I haven't seen change higher volume manufacturing, but it's something I'm really excited about. So it's done amazing things for going from the idea to the prototype. But the challenges with 3D printing, which I'm hoping, or let's say I'm optimistic they'll be overcome in the next couple of years. I'm always an optimist. Is one, cycle time. So for injection molding, we usually do about a 30 to 45 minute cycle time per shot. Whereas if you think of 3D printing a thing, it's usually a couple hours for it to get done. So it's really too slow to get the volumes. Based on that, injection molding, I can get 7,500 shots a week. And then I can do multiple cavities. Whereas right now, you need a lot of 3D printers to support that sort of volume. And it would also be more expensive when you consider the electricity. Second is if you use FDM, which is like a MakerBot, it does leave a little aesthetic bump on the surface, whereas injection molding, you can do what's called mirror spark, which is just optically clear. And then it's also, 3D printing is not dimensionally stable, so it tends to have pretty significant part variation, or part-to-part variation, whereas injection molding is pretty much every part's exactly the same. And then the last thing with 3D printing, it's not isotropic, so if you pull along the length of the fiber, it's stronger than if you try to pull them apart. But you can imagine if we could get 3D printing to go to be able to address some of those challenges, then it gets rid of tooling. And as we talked about with tooling, that's 6 to 8 weeks and thousands of dollars. So I'm hoping over time it'll get there, but it's not quite, at least for the volumes we build in, it's not quite there yet. What I have seen is people 3D printing the molds. So doing metal 3D printing. The challenge is, though, it doesn't leave a good enough surface finish, so you have to go and touch it with the tool, and by the time you've done that, then you're sort of where you were if you hadn't done it. But it's an amazing time to be alive and see all this stuff evolve. What we've got here is very similar to the last chart, same processes on the left, but on the top what we've done is replace them with the different materials that you can use, from iron to carbon steel, zinc, magnesium, titanium, nickel, and classified it whether red is good in this case, normal process, yellow is doable but not recommended, and then gray is you can't do it. So what you could do is overlay the last chart up here where we went through all the different options, and then for these 6, pick which materials would be applicable. And that's where you'd factor in the environmental considerations. So on the part slide, we said we wanted it to operate up to 500 degrees Fahrenheit, let's say, and survive in a bath of light acids and bases. So you may find some materials aren't conducive to that, and then you disqualify those. So based on that, these are our 6 different options. And you may look at that and say, well, these are all options, but really for what I'm trying to do, extrusion makes the most sense when I look at it, assuming you wanted it to be metal. It's a classic extruded shape. Or wire EDM, depending on how thick it is. So once you've got your processes, then with each process, there's different parameters to consider. So for example, extrusion, usually you're going to have a very large lot size, just due to the setup involved and so on, but your die cost is going to be relatively low. So if that matched with what you're trying to build, that's a great option. Whereas wire EDM is great for low volume, and there's very little setup time, but it does take a fair amount of time to machine it. So this is a place where you determine, as a function of volume and cost, which process makes the most sense for what you're trying to do. And then basically, as we talked about, you can just work through each process and rate it according to these different parameters. If you dig deeper, and this is straight out of the book, this will give you the next sort of peeling back the onion, the next layer of different capabilities within the process. So for any one of them, if you wanted to know the typical part size, the tolerances you can hold with that, what sort of surface finishes, and then the type of shapes you can do, this is where you go into details and make sure that the process you pick can support what you're trying to do. But it's an amazing resource, and this is one of my favorite charts, just being able to compare injection molding tolerances with die casting and surface finish. It's all right there in front of you. And the Dewhurst book is, it lays it out very clearly. So that's an overview. Any questions?
What are some of the overlying high-level assumptions on this in terms of like quality? I imagine there's all sorts of other variables you could throw in there in terms of the quality. So when you get production in the market, you keep talking.
Right. Yeah, we always boil it down to cost, quality, and schedule, which we think of that project management triangle.
Okay.
And it's trying to optimize for all of those. Like the joke is you can pick 2, and then the third one is the free variable. But the challenge with consumer electronics is, of course, you want to control all 3 of them, and that's where the interesting trade-offs come. But yeah, we would, whatever material process we ended up with, then we'd put it through that filter. And it's a matter, like, running through this example, it took, 5 minutes.
Right.
So to do it for all of your parts is pretty quickly, and it's a great thought exercise just to make sure you're going down the right path. But then you would apply those other filters.
Okay.
And it's something where with experience you usually get to the answer pretty quickly, but it's a great way to survey the different options in front of you. Great, well thank you for coming. Great to have you here, and look forward to seeing you on the next one.